Welcome to the next lecture in Composing with Sound. This lecture is entitled Methods of Composition. The topics that we're going to address in this lecture include nonlinear forms of composition, processes, and algorithms. We'll also introduce ideas around audience and performer interaction and performance systems. And I'll touch on ideas around the use of diagrams, schematic diagrams, and scores. The goals or objectives of this lecture are to encourage you to think about designs for your final project, and also to discuss alternative approaches to organizing sound. And we want to consider programmatic methods of organizing sound. After all, we're using Max, a computer music programming environment. So just to recap on some of the points that we've covered previously, we've introduced sectional forms for composition that employ repetition and development. And these are traditional organizing structures or principles for the approach that we take to conventional musical composition. We've also introduced the idea of through-composed structures, which rely on some internal logic for the selection or sequencing of sound material. And we've also introduced the idea of algorithmic organization for composition, and I used the example of Terry Riley's In C, and we'll look at that in a little bit more detail. So thinking about the idea of algorithms for composition, we can look at Dodge and Jerse's classic text in computer music from 1997. And they said that there are two principal approaches to algorithmic composition with computers. The first is aleatoric or stochastic music, in which events are generated according to the statistical manipulation of random processes. So these are unpredictable or random processes that produce the sequence. Once the algorithms are put in place, it's difficult to predict what the sound of each iteration of the performance will sound like. The second approach is music in which the computer is used to calculate permutations of a set of predetermined compositional elements. So in this approach, we use the computer's capacity to do calculation and sequencing to work out one possible unfolding of a particular composition. To understand why these approaches came to be, it's useful to look at how they relate to pre-computer algorithms. So algorithmic approaches to composition are not new. They go right back to the Baroque period and probably before. All sorts of musical games were used to compose new musical works. And in this lecture, we're going to look back at two pre-computer examples. You might also want to ask yourself, since 1997, what new developments in computer technology might influence the ways that we approach computer music composition? So I want you to just pause the video and consider that question. What new developments in computer technology might be significant today in musical computer systems? Well, I'm hoping you came up with a few answers. One possible answer might be the development of artificial intelligence. There's probably a whole lot of other answers to do with contemporary developments, new means of interacting with the computer, for example, by voice or video. Okay, so let's look a little closer at Terry Riley's In C from 1968. So once again, this is the score. On the left, you see 53 musical fragments. And on the right, we see a set of instructions for how to perform the piece. And here's an example of one rendition of it from the ensemble Bang on a Can All-Stars from 2011. So at this point, I think we've just got up to fragment number 6. And I'm going to stop it there. You can hear the approach that this ensemble has taken to implementing this algorithm, this set of instructions. So one way of analyzing Terry Riley's in C is to rewrite the text instructions as a kind of flowchart diagram, the sort of flowchart that we might to specify what a computer program should do. So the score for in C is really a set of instructions. It follows an approach of what we might call structured improvisation or aleatoric composition. This approach was pioneered by the American composer John Cage. It's a structured improvisation because the structure, the selection of musical fragments is provided, but the rate at which they unfold is determined by the performers themselves. So let's have a look at this flowchart. So we can see two elements here. The first is an algorithm, a set of boxes for instructions, actions, or decisions. And the second is a list of data or resources. So you can see there's a database of 53 melodic units, and they're given an index n, which runs from 1 to 53, a number that represents each of those 53 melodic fragments. And these could be stored in computer memory, for example. The second resource is 35 performers and their instruments. And the final thing that we need is a tempo or a metronome, which could be a conductor or, as we heard in that example, a regular pulse that starts the piece. So let's read through the algorithm. So we start by setting our index number n to 0. Then we proceed to the first action, which is to add 1 to our index, n equals n plus 1. Then we move on to the next instruction, which is to play fragment number n, fragment 1. Once we've played it, we listen out to all the other performers. Have most other performers moved on? We ask ourselves the question. If no, then we play fragment 1 again. If they've all moved on to the next, and the answer is yes, then we ask ourselves another question. Is the current fragment that we're on number 53? And if it's not, then we go back and add 1 to the current fragment and play that. So we'll now be playing fragment number 2. And once we finish playing it, we're listening out to the others, and if they haven't moved on, we play it again in a loop until the answer to the question, have most other players moved on, is yes. We then ask ourselves, have we got to the end yet? Is it number 53? And if the answer is no, we add 1 and move on and play fragment 3. And this process, this sequence, this algorithm is executed until the answer to are we up to number 53 yet is yes, at which point we play number 53, and then we listen out to see if all other players have arrived at 53. If not, we play that fragment again. Ultimately, when we're convinced that all the other players have got to 53, we stop playing. Now you can imagine how we might move on to writing a Max program to execute this algorithm. I'm not quite sure how we do the listening part, but you can see that it's in the form that a computer might be able to execute. So that was an example of an algorithm. Now I'm going to show you another approach to composition, a pre-computer approach to composition, which has been referred to in the literature as process music. And this is another example from the American modernist movement from the middle of the 20th century, the composer Steve Reich's Pendulum music. So this is the score. You can see once again it's a set of written instructions. Not much notation here though. Pendulum music for microphones, amplifiers, speakers, and performers. And I'll read the score out to you. It says, 2, 3, 4 or more microphones are suspended from the ceiling by their cables so that they all hang the same distance from the floor and are all free to swing with a pendular motion. Each microphone's cable is plugged into an amplifier, which is connected to a speaker. Each microphone hangs a few inches directly above or next to its speaker. The performance begins with performers taking each mic, pulling it back like a swing, and then in unison releasing all of them together. Performers then carefully turn up each amplifier just to the point where feedback occurs when a mic swings directly over or next to its speaker. Thus, a series of feedback pulses are heard, which will either be in unison or not, depending on the gradually changing phase relations of the different mic pendulums. Performers then sit down to watch and listen to the process along with the audience. The piece is ended sometime after all mics have come to rest and are feeding back a continuous tone by performers pulling out the power cables of the amplifiers. Okay, so this paints a bit of a picture perhaps. Many of you may have experienced feedback, acoustic feedback, where the signal from a loudspeaker is picked up by a microphone. The output from the microphone is then amplified and sent back to the loudspeaker, and we get this feedback circuit, and it produces a rather unpleasant howling tone. So I'm going to play you an example of Steve Reich's Pendulum music. They don't seem to exactly follow the score, but the general idea is there. Let's have a listen to this. Okay, I'm going to pause it there. We're not going to wait for the piece to get to its final conclusion. I think you get the idea. Phasing was one of the musical interests of Steve Reich, and he wrote several pieces of music with this principle of musical processes of different lengths that unfold together, and so the combinations of those musical phrases would change over time. Okay, so here I want to try and analyze Steve Reich's Pendulum music. The score itself is a set of written instructions, but pendulum music is really a design for a musical system, and we might reimagine the score as a schematic diagram. So here on this slide you can see my schematic diagram with some standard schematic symbols. So this symbol here is the symbol for a microphone. A triangle is an amplifier, and there's two types of amplifiers in this system design, a microphone preamplifier and a power amplifier. And this is the symbol for a loudspeaker. And you can see the signal flow is represented by these solid arrows. Signal flows from the mic to the mic amp, from the mic amp to the power amp, out of the power amp and into the loudspeaker. And the dotted curve here is meant to indicate the motion of the microphone in front of the loudspeaker. So this schematic diagram is another way of representing this musical design. So to recap, we've considered algorithmic processes as approaches to composition. We've thought a little bit about graphical scores and system diagrams. I want to encourage you to think about sketching musical systems as a useful tool for making musical design ideas, to make them more concrete and as a step forward to realizing a max patch. So these two diagrams are produced with a free drawing tool called draw.io or diagrams.net. It's a great, simple to use and quite powerful diagramming tool, but you know, a pencil and paper are equally powerful. And in some ways, scribbling with a pencil and paper is a great way to try out ideas, to develop and resolve problems, identify problems, and find solutions for them. Okay, so now moving on, I want to introduce another approach to musical composition that we might call open frames or interactives. An obvious use of Max is to build novel signal processing systems. For example, a custom guitar pedal or a vocal process. And these can be exploited to develop new timbres in instrumental or vocal composition. Another approach might be to use that power of Max, the signal processing power, to develop systems that might open out to the audience for audience interaction or for installation by designing systems that people can play. And this example here called soundboards is one that presents this kind of approach. So you might have noted that the Steve Reich's pendulum music example was presented in what appeared to be an art gallery. And this was quite a common thing that happened in the 1960s, musicians moving out of the concert hall and into art galleries. The advantage of the art gallery is that it addressed a more open and accepting kind of audience, and also the conventions of concert performance, the separation of the audience and the performers was broken down in the context of the art gallery. And so in this example, we see another kind of gallery installation where the audience is invited to play with the system. And in this video, we get to see that kind of approach. Okay, I really like this example. I mean, you might be able to detect some of the signal processing effects that are used in this, some granular synthesis, some pitch shifting and delay. I really like the way that normal household objects, this crockery, are transformed into a kind of engaging visual display, but also that they produce this really engaging oral display and they invite a kind of performance approach. Okay, now I want to look at some of the features of algorithmic design, particularly the idea of data stores, conditional logic, and the random sieve algorithm. So the patch that we can see on the display here is the patch that's used to create the video title screens for this lecture series. The simplest data store in Max is the coll object or collection. A coll can be used to store and recall indexed values and lists. And so you can see there's a coll object there called text, which contains values that represent the characters that are typed out on the screen. A metronome and a counter are used to recall the letters and play sounds corresponding to each letter type. A subpatch called key clicks looks for the space character, which is character number 32, using the select object and plays a different sound every time a space character is displayed. The select object is used to implement what's known as conditional logic. We might rewrite its function as a pseudocode. If the character equals space, play frequency 1000 Hz, else play frequency 500 Hz. So for every letter character, we hear a click centered at 500 Hz, and for every space, we hear a click centered at 1000 Hz. So looking more closely at the coll object, it's an indexed list of messages. Any message can be stored. For example, we could store note values for a melody. So in this example, we can see each row first has an index number, 1, 2, 3, 4, 5, followed by a comma, and then a list of 3 values which could be used to represent pitch, velocity, and duration of a note. Each row in the coll object is terminated with a semicolon. This is just the way the coll object works. And when we put an index number into the input of the coll, we get the message, in this case a list of 3 numbers, come out of the coll. So in this patch, I'm going to demonstrate a sequenced melody, randomly selected notes from a melody, probability-based voice selection, and a probability-based rhythm using the random sieve algorithm. Okay, so let's look at this patch in operation. We can set the BPM, so let's start with 250 beats per minute. And we click the metronome, we click the toggle to start the metronome. So we can see the counter counting from 1 to 24 each time it receives a bang, and here we get a number. That number is entered into the first inlet of the coll object, which acts as an index, and when that index is received, the coll object spits out this set of 3 values. This list of 3 values is unpacked into a make note object, which provides the duration. The pitch and velocity are repacked into a 2-number list, and you can see that list coming out here, and that enters into a synth subpatch and then out to the output. Let's just explore this a little bit more closely. So you can see I can enter a number into the index for the coll, and it produces one of the lists of values. If we open the coll object, it displays the data stored in a text file called melody.txt. And there are 24 lines, and these three numbers represent pitch, velocity, and duration. So the first note goes for 1 second, the next note goes for half a second, and the next note is very short, 60 milliseconds. So let's just cycle through some of those lines. You can see those appearing here in the message box. And as I said, they're passed into a makeNote object, which produces a pitch and a duration, and importantly produces a 0 for a note off at the end of the duration of each note. So there's the pitch number 65 with the velocity of 0 to say turn the note off. And the sound is produced by this simple polysynth patch. And here's the simple polysynth patch using the poly object so that we can get polyphony. Okay, so that's a little bit of fun. So that's using the coll object as a data store, and in this case, it's storing a sequenced melody. Now, our next patch takes the features of that patch and augments them with, instead of a counter, using a random number generator, which produces a number from 0 to 23, and we add 1 to get a range from 1 to 24. And we use that to drive the index of the coll object, and the rest of the patch is the same. So let's set our tempo, 250 beats per minute, and let's see what this does. So these are the same notes from the same collection of notes, but instead of playing out in that melodic sequence, they're played out in a random order. Okay, so this is another way of using the same data, but with unpredictable sequence of notes. Now, in this patch, we augment this design once more, but we use an algorithm called a random sieve. So once again, we have a metronome producing a regular series of bangs. Let's set the tempo there, 240 beats per minute. And this time we have a counter again that's counting from 1 to 24. Now the trigger object is used to sequence the order with which messages are produced, and it can also be used to replace one kind of message with another. So in this example, the integer number that's coming in is replaced with a bang, which goes out first, and that triggers a random number generator, which produces a number between 0 and 100. And then once that bang has gone out, the original integer number is passed through. Now you can't see because of the way the patch is designed here, but that integer is passed into this gate object. This is a graphic gate, and a 0 as the gate closed in this way, and 1 has it switched through to the other outlet. Okay, so now we've got some logic here. So we've got a random number somewhere between 0 and 100. This comparison operator says if the number coming in is greater than 50, let's turn the gate on, and if it's less than 100, less than 50, let's turn the gate off. So the output here is a 0 or a 1 to report on the logical condition of the number coming in. And we can change the probability by replacing the 50, which gives us a 50-50 chance of it being more or less, with some other probability. Now, what does the probability do? Well, if the value is less than 0, then the integer is passed on to this side. And once again, we have our melody collection of notes and a simple polysynth, the same instrument that we had before. If the value is greater than 50, then the switch is switched, and instead we get the same melody, but played with a different synthesizer, an FM polysynth. Now let's see what that sounds like. Turn the volume up here. You can see our graphic switching here. So you can hear the FM synth is a rather inharmonic sound. Let's just quickly have a look at the synth. There it is. It has an FM synthesizer built into it rather than the harmonic synthesizer that we had on this side. Now let's just change the probability here. I'm going to make it less likely. If the number is less than, let's say, 90, we'll get the inharmonic sound. And I can make it mainly the inharmonic sound by saying if the number is less than 10, and I can make it 100% probability that it will be the harmonic sound, because every number is going to be less than 100. And I can make it 100% probable that it'll be the inharmonic sound by setting this percentage to 0. And we can set it back to toss of a coin, 50-50. Perhaps every second note would be of an inharmonic character. So there are 101 applications for this random sieve algorithm, and we can control the probability. And let's just see what happens in our next patch. Okay, in this patch we have two random sieves, and we have two synth subpatches. This one's called hat closed, and it uses noise and a filter to create a sound like this. And we have another patch called snare, which uses similar sort of synthesis approach, and it has a tone and some filtered noise, and it produces a sound like this. And now we want to decide whether we have a hi-hat or a snare. So let's set this going, and we want 100% chance of having a closed hi-hat and maybe a 50% chance of a snare. Let's change that probability and say we're going to have a snare on every hit and a 50% chance of a hi-hat. Now that's pretty boring on the snare. Let's make it 80%. Still pretty boring. And let's have a few more hi-hats. So you can see we get a bit of a groove happening there, a totally random groove, using the random sieve algorithm to create a rhythm. The Exploring Coll patch is in the Patches folder on UTS Online. Grab yourself a copy and have a play. So just to recap on that demonstration, we saw a sequenced melody, randomly selected notes from a melody, a probability-based voice selection patch using the random sieve, and then a probability-based rhythm where the selection of one or other instrument timbre was determined by one or other random sieve algorithm. So now we're going to take the random sieve and develop it a little bit more with a more detailed step sequencer. So many of you may be familiar with the step sequencer. It's really the fundamental design of the original drum machine. And this patch has 1, 2, 3, 4, 5, 6 voices, which are very simple subtractive synthesis patches. And we can set the probability that we'll get one or other of these sound types on each pulse as the patch counts through the pulses. Okay, so let's have a little play with this patch. We can set the tempo, 120 beats per minute, and we turn the drum machine on, and you can see we've got 16 individual pulses divided into 4 units, which we might think of each unit as being a crotchet, and each of the 16 as being a semiquaver. So we can use this as a conventional step sequencer by enabling a sound, let's say a kick drum on every beat, and a typical rock beat would give us a snare drum on the off beats. And typically we'd have a closed hi-hat on every quaver beat. Let's turn those on. Okay, and maybe an open hi-hat on the first beat of the bar. So we're in some fairly conventional territory here. Let's have some of these funny tom sounds. Okay, you get the idea. So we're making a rhythmic pattern here. Okay, so this is nothing that we can't do with any old step sequencer. Now, the numbers in here set the probability that we're going to get a note on each one of these beats. So I guess we want 100% probability for a kick drum on the crotchet of each beat. So let's do that. And let's add a 50% chance that we'll get a syncopated kick drum there. And let's sort these closed hats out a little bit. Let's say we want an 80% chance of one on every other note here. And you can start to hear this pattern unfolding. Bit of a groove going on, unpredictable groove. Okay, and let's spice up these toms just a little bit. So get rid of these ones. And I can see there's a bit of a problem with the colouring that I've programmed into this. Colours seem to not be resetting for some reason. And the probability is a little bit too high here, so let's change that. Okay, I think you're getting the idea here. And let's just get rid of these guys. Make them a bit more unpredictable. And so it's almost 100% likely, 90% that we want one on. Okay, so this is using the random sieve algorithm, but each individual note in the step sequencer is determined randomly, and this gives us the ability to make this kind of pattern. And you can see that's a little bit of fun there. Okay, just to recap on where we've been, we've thought about non-linear forms, processes and algorithms, and we've compared traditional ways or ways in the 20th century music literature to achieve these kinds of musical outcomes with processes that are implemented as algorithms in the computer. I've given you an example of an audience or performer interaction performance system. We haven't built any patches around that approach, but you might imagine approaches to doing that. The idea of using the max patch as a kind of signal processing device requires that you use an audio interface. We haven't looked at audio interfaces yet, although you'll find there's a video in the selection of videos that demonstrates that process. I've suggested the use of sketching, scores or schematics, diagrams, scribbling with pencil on paper as a way of developing your ideas before you start implementing them in a patch. And I hope that that's got you thinking about where you might be headed, some approaches to where you might be headed in your final project. We'll have more examples to see as the semester goes on. And to kind of make some of these ideas about alternative approaches to organizing sound a little bit more concrete and perhaps a little bit more attractive than the rather dry plink-plonk music from the 1950s that we heard at the beginning of the semester. And to just get you thinking about how algorithmic or programmatic approaches to organizing sound might be applied in interesting musical contexts. There's some useful references that you might want to follow up. And that concludes the lecture. Store up your questions, ask them straight after the lecture, or perhaps store them up for the tutorial. I look forward to seeing you in the tutorial. I hope you enjoyed that lecture. See you next time.